Okay, so in this video we're going to look at finding the area between two curves using definite integrals. To find the area under a single curve bound by a graph, look at the other video that's coming out for definite integrals, area under curves, but we're going to look at area between two curves in this one. Now essentially I've got a few different scenarios here, but don't follow these ones exactly, but we've got a couple cases that have single areas and one with a double area. So this first case, you've got an area fully enclosed. You'll probably hear the word bound by the graphs of g of x and f of x. Now the way to find this area between those two graphs is to find the integral of the top one minus the integral of the bottom one. And that's what I've written down here. So you've got the top function minus the bottom function. The next case we can look at is where the g of x is now on top. So now I've got the orange one above the blue one, but it still remains the same in the sense of it's always the top function minus the bottom function. So it's not a matter of having a preference of f of x always goes above. It's always whichever function is the top version will go over the top of whatever the bottom one is. It's always top minus the bottom. Of course, these graphs do change over top and bottom sometimes, so you can see here. This one here, the blue is on top, but this one here, the orange is on top. And that will mean you'll have to have two separate integrals, just like when you're doing area underneath the curve individually when it goes below the axis. You have to have two separate sections. Same happens here, but it's not when there's anything with an axis, it's when they intersect each other. So you must break these graphs up to find the areas, break them up at their intersection points. In this case here, when it goes below the axis, it doesn't matter. So don't worry about it. Don't try to split up at the x-intercepts. With area between curves, you only split based on the intercepts. And that's it. You can also be asked to find this area out here. It just won't be bound by both curves by itself. It'll be bound by g of x and f of x as well as an extra line, rather than just bound by the two curves. So you can certainly find extra areas. Let's have a go with two examples. Find the area bound by the lines y equals sine of x and y equals x plus 1 and the line x equals pi. So let's have a look at what these graphs looks like. It's always good to look to what graphs look like. Makes your life a whole lot easier when you're trying to draw things. So sine of x does this, like that, and x plus 1 does this. And I'm asked to find the area of, so that tracks back and that course keeps going. I'm asked to find the area between those two and the line x equals pi. Now, this is a standard sine graph. The period is 2 pi. So half a pi is there. So I asked to find all that in there. And I actually wanted to put an extra thing saying we want to stop at x equals 0. I'll put in here, otherwise we'll be here forever, literally. So I'm trying to find this area in here. So writing the integral is going to be between, well, the smallest x value we have here is 0 and the biggest x value is pi. So between 0 and pi of the top function, which is x plus 1, you can see that's above the other one, minus the bottom function of sine of x. And I put brackets around all of that. And at this point, I integrate and solve. So x becomes x squared over 2, 1 becomes x, negative sign becomes positive cosine. You need to know your integration rules to do this clearly. And we substitute 0 and pi in. So pi goes in, you get pi squared over 2 plus pi plus cosine of pi minus, put brackets in, 0 goes in, and you do 0 squared on 2, 0, 0, and cosine of 0 is all that's left. And we simplify. Pi squared on 2 has no other like terms. Pi has no other like terms, but cosine of pi we know is negative 1. And cosine of 0 is 1. So we have negative 1 minus 1 gives you negative 2, and that'll be units squared. Our second and final example here. So we're going to this time have the lines y equals x, x squared, and the line x equals 2. So drawing y equals x just does this. It actually goes through the origin. Let's try it again. Y equals x squared does this. A very good parabola, don't tell your maths teachers. Something like that. It's not quite right, but it does that. And then we're asked to find it up to 2. Well, that's 0. That's clearly 0 there. And then the line x equals 2 is going to be about here somewhere. This intersection happens at 1. Now, you can see that the parabola, I should change the color of the linear equation so you can see it a bit more clearly. The parabola is below the linear between 0 and 1 and above the linear between 1 and 2. So we must split this into 2 integrals. Now let's just confirm that the intersection of these 2 graphs indeed 0 and 1 the way I've drawn it. The way you do it is you'd solve simultaneous equations. So you know x squared must be equal to x. Do not divide by x, please. Make sure you use factorizing to solve this thing. The null factor law gives you 0 and 1. If you divide by x here, you're left with x equals 1 and you've lost your 0 solution, so please don't do that. So you can see that coordinate there is 1 and it's actually 1, 1. So to find the area, you need to do the integral of the yellow one, which is x, minus the area of the integral of the blue one, dx, and we need to do that between 0 and 1. Then we're going to add that to the integral between 1 and 2 of, this time the blue one is on top, x squared, minus the yellow one of x. Sorry, I should have shaded in this little area in here and that there in there so we can see what's going on. Once we've got that, we now integrate and solve. So x becomes x squared over 2, x squared becomes x cubed over 3 between 0 and 1, plus, again, x cubed over 3 minus x squared over 2 between 1 and 2. We substitute our values in, so 1 goes in here, becomes 1 squared, which is 1 over 2, minus 1 cubed of 1 over 3, minus, put 0 in there, we get 0. 2 goes in, you get 2 cubed, which is 8 over 3, 2 squared, which is 4, 4 over 2 is 2, so minus 2, minus 1 goes in, you get a cubed, that's a cube, 1 cubed, which is 1/3, when it's divided by 3, and you get 1 squared over 2 like that. And that's a matter of simplifying all of it. So we have 8 over 3 minus 1 over 3 give you 7 over 3. You have minus a half, you have minus 2, and here you get minus 1/3 plus a half, and you'll, oh, that should be positive half there, sorry. So 7/3 minus 1/3 is 6/3, which gives you 2. 1/2 plus 1/2 is 1, and then minus 2, and that all gives you 1 unit squared. So the key, remember, is to find the top function and subtract it from the bottom function. Just to clarify, these two here go together, and these two here go together. And that is how you find the area between 2 curves.